Hello students, I welcome you all once again. In the previous class, we have learned factors affecting stability of complexes. Okay, so in that class, I have taught you the first four factors, that is nature of central metal ion, second one electronegativity of central metal ion, third one electronic configuration of central metal ion, and fourth one is nature of ligand. Okay, so in this class we will be learning from the fifth factor, and the fifth factor is cyclisation or chelation. Okay, this is the fifth factor which affects the stability of complexes. So what exactly is under chelation or cyclisation? Cyclic complexes are more stable when compared to acyclic complexes. Okay, so for example, look here in the diagram or the figure given below. Cyclic complex is CuEn twice plus 2, okay, which is more stable than CuNH3 4 times plus 2. Why CuEn twice plus 2 is more stable, students? Because it is cyclic, whereas CuNH3 4 times plus 2 is not cyclic. Okay, comparatively, the first complex, that is CuEn twice plus 2, is highly stable when compared to CuNH3 4 times plus 2. Okay, students. So this is about cyclisation or chelation. What is that you have learned under this factor, students? The cyclic complexes will be more stable than acyclic complexes. Okay. Next, sixth factor is effective atomic number rule. What is this effective atomic number rule? And how does this factor affect the stability of the complexes? The complexes which obey EAN rule, that is effective atomic number rule, are more stable than the complexes which do not obey EAN rule. Okay, so here if you observe the example given here, nickel tetracarbonyl, that is NiCO4, has effective atomic number of 36, which is more stable than NiNH3 4 times plus 2, whose EAN is 34. Okay, so NiCO4 is more stable than NiNH3 4 times plus 2. Okay, so this is what you are supposed to write under EAN rule, students. The complexes which obey EAN rule are relatively more stable than the complexes which do not obey EAN rule. This is the sixth factor. Next, coming to seventh factor, crystal field stabilization energy. Shortly, we call it as CFSE. What is that, students? Crystal field stabilization energy. Under this factor, we learn that the complexes having high crystal field stabilization energy values will be more stable than the complexes having lower CFSE value. Okay, so the complexes with high CFSE values will be more stable than the complexes with the lower CFSE values. For example, FeCN6-4 has got its CFSE value as minus 2.4 delta O, whereas CONH3 6 times plus 3 got its CFSE value as minus 0.4 delta O. Okay, so comparatively among these two complexes, FeCN6-4 will be more stable as its CFSE value is higher than the other complex. Okay, so this is what you are supposed to write under crystal field stabilization energy. Okay, students, the complexes of higher crystal field stabilization energy are relatively more stable than the complexes of lower CFSE values. Clear? So this is the seventh factor. Next, eighth factor, temperature and pressure. That is effect of environmental factors like temperature and pressure. So under temperature and pressure, we learned that the compounds containing volatile groups or ligands like water, ammonia and ethylene diamine are less stable at high temperatures, and on heating they undergo decomposition. What is that, students? The compounds containing volatile coordinating groups, that is volatile ligands like water, ammonia and ethylene diamine. Such complex compounds are less stable at high temperatures, and what happens if they are heated? They undergo decomposition. Okay, so I have given an example here. The hydrates on heating lose water, CONH36Cl3 loses ammonia, and CrEn thrice Cl3 loses ethylene diamine on heating. What did we learn under temperature, students? The compounds or the complex compounds which contain volatile ligands. For example, water, ammonia and ethylene diamine. They are found to be less stable at high temperatures, and when such complexes are being heated, they undergo decomposition. Okay. For example, kindly observe here, the hydrates on heating lose water, CONH36Cl3 on heating loses ammonia, and CrEn thrice Cl3 on heating loses ethylene diamine. Okay. So look at the reactions given below. CONH36Cl3 gives CONH3 5 times Cl2 plus NH3 when heated up to 180, that means from 175 to 180 degrees centigrade. Okay, so ammonia is being lost by the complex CONH36Cl3 when it is heated from 175 to 180 degrees centigrade. Similarly, CrEn thrice Cl3 when heated up to 210 degrees centigrade, it loses ethylene diamine. So, what are the compounds formed here, students? CrEn twice Cl2 Cl plus En. Okay. So, this is the effect of temperature. Also, if you observe certain coordination compounds, they are changed from one form to other. That means they change their form. For example, AgHg, AgI4, which is a red colored complex, it turns into yellow colored Ag2HgI4. And the temperature, at what temperature it is being converted from red to yellow, students? When heated up to 45 degrees centigrade. Okay, so this is the effect of temperature on stability of complexes. And also reduction in pressure results in loss of volatile compounds. Same what we have learned under temperature. Okay, so when pressure is reduced, we find loss of volatile components from complex compounds. Okay, students, this is about temperature and pressure, how they affect stability of complex compounds. And the last one, that is ninth factor, concentration. There are many complexes which exist in water only in the presence of high concentration of coordinating particles. Okay, so we find few complexes which can exist in water only in the presence of high concentration of the coordinating particles. Okay, so what do you understand here, students? Many complexes, they can exist in water only when the concentration of coordinating particles is very high. Okay, what is the reason for this? Because water molecules have greater coordinating tendencies than the molecules or ions which are originally present. This is the reason why many complexes, they can exist in water. What is the reason, students? The water molecules have greater coordinating tendency than the molecules or ions which are originally present. Okay, hence the complexes can exist in water only when the concentration of coordinating particles is very high. For example, CuCl4-2, which is in yellow color. So originally it is an yellow color solid. When dissolved in water, what happens? It is being converted into a pale blue hydrate of copper 2 ion, okay, which when excess of HCl is added, it gives back the yellow colored CuCl4 minus 2 complex ion. Again students, CuCl4 minus 2. Originally it is an yellow color solid, okay, but when it is dissolved in water, it converts into a pale blue colored hydrate of copper 2 ion. Okay, so when you are adding excess of chloride ion, for example, if you add HCl to this pale blue color hydrate of copper 2 ion, it gives back the yellow colored complex ion, that is CuCl4 minus 2. Okay, so this is about concentration which is affecting the stability of complexes. Okay students, so kindly check the or watch the previous video in which I have given you 4 factors, and all the remaining factors I have done in this class. Okay, so kindly watch these 2 videos and please write down all the factors affecting stability or stability constant of complexes in your notebook and read all the factors. Hope I made the factors very easy and clear to you students. Okay, so thank you.